Hi, this is Julian. I'm going to be doing a quick code run-through of the game that I made, or example program that I wrote for the NES. I want to start off by giving a short example of what the program can do. So basically it loads up a little Mario sprite, and you can use the directional pad to move the sprite around, which is pretty simple. Or you can press the A button to do a little jump, and it clips around. So that's all it does. It's a very simple program, but it shows a lot of the sort of core things that the NES is able to do. I will start off by saying that I did start with example code that I found online, but I researched it really thoroughly and feel like I understand in pretty good detail what every line does now, and hopefully you'll see that with my explanation. But when I got the code, all it would do is load a sprite, and you could press A to move a quarter of the sprite left or right. So I modified it so that it moved the whole thing rather than just the top left corner, and I gave it directional freedom, and of course the jumping was all custom coded by me. The jumping ended up being like half the work, with the other half of the work being understanding most of the example code and getting to the point where I felt like I could modify it freely and do things like change the background and change the color palette that Mario was loading with, because he originally loaded up with really ugly color palette. So anyways, let's go ahead and start digging into the code. So this is the assembly file for the NES game. You can see it's pretty short as far as assembly files go, maybe a couple hundred lines. Yeah, around 300 lines. And I'm basically going to just start with a overview of what this assembly file is doing. So if we remember from my NES presentation, the overall architecture of the NES is in two parts. There's the NES itself and the cartridge. So the NES has CPU for processing, APU for audio, which I don't work with at all, and a PPU for pixel processing for graphics. And the cartridge itself has program ROM and character ROM for the code and the graphics. I don't mess with WRAM, it's for save states, and the lockout chip is all on the emulator, and that's stuff I don't have to worry about. So everything I'm writing for my assembly code is going on the cartridge, either in program ROM or character ROM, and I need to be explicit about whether it goes into program ROM or character ROM, but that's what all this assembly is doing, is it's all getting assembled down and then being turned into a ROM file, which is acting as a emulated cartridge. And so the reason why this assembly file is written the way it is because I'm targeting a particular assembler called NES ASM3, which is the standard emulator assembler. Back in the day when they were flashing this data onto ROM and actually soldering that onto cartridges, they would have had different assemblers that would have had the program of the character be outputted separately and stuff like that. But now we're basically just worrying about emulators, because that's the only reasonable way of doing this. So the overall structure of this code is basically that the NES works on interrupts. So when the cartridge is put into the system and the power is flipped on, what the NES does first is it checks for where the reset vector has been defined. So if we go over here to the memory diagram right here, we can see that this is all the memory that the NES can address between FFFA and FFFF. there are these three special vectors: NMI, reset, and IRQ. So these three vectors are essentially registers that hold memory addresses that point to labels that should be called when various interrupts happen. So the reset vector needs to be set by the programmer to tell the NES what address it should look for when the power gets flipped on or the reset button gets pushed. And the NMI vector needs to be set to let the NES know where it should look for code to run when a vertical blank happens. In other words, when it has some time to update the sprites and move things around the screen without causing clipping to happen. I'm not sure what the IRQ vector does. All the tutorials I looked at said that it's not very relevant and doesn't come up a lot, so I didn't end up looking into it. So when the NES gets powered on, the way that this code gets entered into is through that vector. So the first thing that needs to happen is actually at the bottom of this code, and it's defining those vectors. So the vectors are defined right here on these 4 lines. What these 4 lines do are they set the program counter, and then they set those 3 memory addresses so that the NES knows where to look when those interrupts happen. So the way that it sets the program counter is with the .org assembler directive. Everything that starts with a period is an assembler directive and not an actual instruction in 6502 assembly. So .org FFFA says that we want the following code to be written onto the cartridge at FFFA, which is the start of these vectors as we looked at previously. So then we're using the assembler directive .dw for define word, and what that does is just writes whatever comes after it. In this case, NMI is a label that's going to point to a certain memory address, very similar to MIPS assembly and ARM and stuff like that. So basically, starting at FFA, we define the word for NMI to tell what this vector should be defined as. In other words, it should know what address NMI starts at, and then we define the word for reset, similarly letting the NS know what address it should look at to run reset code, and we don't bother with defining IRQ, we just set it to 0, because it's not used for my purposes. So now, with these 3 vectors set, the NES knows what labels to look at. Reset and NMI are not special names, they're just labels, so if I wanted to break my code, I could change reset to be, sprites. And then, rather than looking at reset, it would go up to this sprites and run this code, and that would be bad. Wouldn't work. But as it stands, it looks up to these labels up here. So reset NMI label is right here. This is for all of the sprite update and game engine updates, and reset label is right here. So system gets turned on, reset label gets hit, but before that we have a header. This is all assembler level stuff, completely ignored by the NES, but very, very important for the assembler. This very, very top 4 lines is the ROM header. Again, you can see it starts with periods, meaning these are all assembler directives, basically just telling the assembler how much data you're using. So this small piece of example code is just using 16 kilobytes of code program data, 8 kilobytes of character data, and no mapper, and it's using background mirroring. Background mirroring isn't at all relevant to what we do here because we don't define any backgrounds, but that has to do with shifting backgrounds forward and backward in sort of 3-dimensional space. Mappers were something I didn't mention too much in detail. Basically, they were they're a virtual memory sort of technique, and we don't use it for this because our code is so small that it fits inside of the 32K. That, in fact, we're only using 24K. So if we wanted, we could have an extra K of character data, but we're not going to bother with that. All data on the NES is split into 8 kilobyte banks. You can think of these as pages in an operating system's sense. So we've got 2 banks. The first 2 banks are program, and the third bank is character data. That'll be relevant later on. And then we set up some variables. RSSet is another in some assembler directive that tells the assembler basically we're going to be reserving some space for variables. And we're telling it that we want it to start at 0000, which is the start of the internal RAM for the CPU. So I'm fairly certain that that is this RAM right here on the physical NES. So it does have some extra RAM that is not on the cartridge. So we're storing some variables into that internal RAM. The first variable is jumping. That's to make sure that when Mario is in flight, he doesn't have the ability to jump again. And then also the Y velocity. I actually chose to use a velocity for the jump rather than having it hard-coded in some other way, and it gives it a somewhat realistic parabolic motion, which is pretty to look at. And so what these variable definitions are doing is it gives it a name, and then .rs means reserve space, and 1 is how many bytes. So we're reserving 1 byte for the boolean is jumping and 1 byte for Y velocity. You can't reserve space at anything lower than the byte level, otherwise is jumping would have been 1 bit. These are just a couple of constants. They work just like C pound define, in that it just, the assembler before it even, during the preprocessing step for the assembler, it goes through and it replaces all instances of each of these with the values on the right. Very straightforward way of dealing with constants. So, starting at the very top, we can see that we're starting with reset. So this is when the NES gets turned on, it's going to go to this reset label because we set that vector. Here we use the assembler directive .bank, which tells it which bank of the the cartridge that we want to be writing into. So banks 0 and 1 are going to be program data, bank 2 is going to be character data. So here we're saying, please write into the first half of program data. So that's going to be somewhere in here. And we set the program counter using .org to C0000. That is not special at all. It's just somewhere in cartridge ROM that's we know is safe and doesn't have anything going on in it for where we're going to save our reset code. So what reset does in this whole big block, with a lot of strange and specific commands, is it's basically just disabling everything. It disables the APU, it disables NMI, it disables rendering, the IRQs, everything, because while we're setting up all variables upon reset, we don't want any interrupts happening. So, for example, if I got rid of this line that disables NMI, then it would be possible for, while we're getting our memory all set up, essentially when we're loading the game initially, a vertical blank could happen and we could get interrupted and it would throw everything off because we were totally not ready to write anything to the PPU and it would just get messy. So while you're resetting, you disable all the various interrupts that could possibly happen, and then you have to wait for NMI. Basically you're waiting for a vertical blank just to make sure the PPU is up and running just fine, because you're going to be interacting with the pixel processing unit soon. So this is doing a bitwise test on 2002, which if we jump over here is one of the PPU I/O ports. This is a status port for the PPU, so you sit here and wait until the status port tells you that the PPU itself is up, and then you branch plus. In other words, BPL is branch plus. You branch when it's not up. When the status is given as plus, that means that you need to branch back up and to continue to wait. And once we're done waiting here, we clear out the memory. This is weird, scary looking code, but all it's doing is loading into the accumulator the value 0. So basically this assembly, almost everything works on the accumulator. So as a refresher from my presentation, there are 5 registers, A, X, Y, stack, and status. Pretty much, for my purposes, I only use A and X. A is the accumulator, and it's where you do all of your operations. So like, for example, the opcode AND, if you just call AND and then a number, it implicitly ANDs that number with the accumulator. And so if you want to work with the X register, you usually have to load X onto the accumulator and then work with it and then load it back onto X. So yeah, basically everything is happening on this accumulator. So when we load onto the accumulator. You can also do LDX to load onto X, but everything like add with carry, ADC, you just do ADC and a number, and then it implicitly adds that number to the accumulator and stores the result back to the accumulator. But anyways, that's a bit of a tangent. So pound means immediate value, so it's doing a literal. Money sign means hex, so we're doing loading onto the accumulator 0. We're just zeroing out the accumulator, and then we're storing the accumulator STA onto a bunch of different memory values all at once, and then we're incrementing X. So it first stores it onto 00000 plus X, comma X here means store the accumulator onto this memory address, in other words 0000 plus X, and we're incrementing X until X hits FF, meaning basically, you know, to sum this whole loop up, it sets the values for 0000 through 0800 to be all 0. So jumping back here, all of this internal RAM is getting zeroed out. So that's all it's doing. And then initializing some variables. This was code that I wrote actually. Just initializing is jumping and y velocity to be 0. And now we wait again for the PPU to make sure that it's ready to receive data. I feel like this is probably more of a paranoia check than anything, but you know, it was in the original tutorial and didn't want to remove it. Now we get into the sort of meat and bones of it. We start loading palettes and loading sprites, but before we can talk about loading those, we need to look at where these palettes and sprites actually are. So at the bottom of the code, we actually define these palettes and sprites in a very particular way. So the palettes and the sprites are all defined in here. I'm not going to get into too much detail about what a palette is and what a sprite is, because I covered that in my presentation, I guess very briefly I can show the slide. I might have, oh yeah. So, the palette is this table over here. The sprite is a pattern table entry with an attribute table, and that's how it indexes into this palette to decide what pixel is what color. That's all the review I really want to do. I don't think that's very incredibly necessary to understand. So this entire block of code first sets the bank to be 1, so we're in the second half of program ROM, and then it sets the program counter to be E0000. This is completely arbitrary. It's just a spot that we know is going to be blank in character ROM, or sorry, in the cartridge ROM. And then it has this label palette, which is just to make it so that later in the assembly code we can refer to palette and get this memory address back, much like in MIPS. This label is just a memory address, and it's in particular going to refer to E0000, and then we do .db, another assembler directive, to define a bunch of bytes. And so this is the background palette, which is completely unused for this tutorial, but this is the sprite palette, and it defines every color in the sprite palette for indexing. So basically the palette is stored into the into cartridge ROM at E0000, and then it needs to get loaded into the PPU before it can be used. So all of this, after this code runs, the palette is just sitting on the cartridge. Similarly, this sprite's label sets a memory address, and then we define these 4 bytes to say how we're going to index into a bit of sprite data, a sprite sheet that we had defined. So what each of these 4 bytes is doing is, the way that a sprite is defined is, so every sprite, as we can see from back over here, is, every sprite is an 8 pixel by 8 pixel array, and it has an attribute table entry, and that's how you index into this palette, as I just mentioned. So this second number is which 8 pixel by 8 pixel tile should be used out of the binary data that we loaded into character ROM. So we're using 32, 33, 34, which is the 4 corners of Mario. So each part of like his head is in 2 separate 8 by 8 pixel tiles. This 01 is the attribute. It tells the upper 2 bits of the palette, so that means that we're going to index into here when we check the pattern table entries. And this on the left is the Y position on screen, so 80, and this on the right is the X position. So when we're manipulating this later, what we're going to do is we're going to take this sprite data and this palette data, load it into the PPU's memory, and then we're going to modify it from within the PPU once it's loaded onto there. You might be wondering where these sprites are coming from. We've at the very, very bottom, we have this .bank2, so now we're actually looking at character ROM, and we set the program counter to be 0, and then we just use this assembler directive incbin for mario.chr. So what this is going to do is just dump the binary file mario.chr, which contains a palette table for Super Mario Brothers at starting at memory 0 on the character ROM. So that's where these tiles are all coming from. So after all this code runs, we have palettes and sprites on the cartridge starting at E000, and we need to get them onto the PPU for them to be properly read. So basically that's what load palettes does, is we first make sure the PPU is all ready by checking a latch. I won't get into that. And then we tell it that the address we want to look at is 3F00, which should probably be 3000. Yeah, I'm not entirely sure why that address is as it is, to be honest, but oh yeah, so 3F00 here is a pointer into the PPU. So the PPU, the way that you interact with it is you basically tell it where it should be writing to itself, and then you give it data, and every time you give it data, it moves its pointer forward. So right here we're saying that it should be writing into 3F00 because if we look back at this, we can see that between 2000 and 4000 is the PPU I/O ports, and 3F00, oh actually what we want to be looking at is PPU memory. So so if we look at the PPU memory and we look up at 3F00, we see that it has the background palette, and 3F10 is the sprite palette. So essentially what we're doing is telling the PPU that it should be pointing at 3F00, where the background palette needs to go in the PPU, and then it'll automatically increment to 3F10, where the sprite palette needs to go. So we tell it, okay, we're writing at 3F00, and then we have this load palettes loop that just keeps firing data, and that data will get written to 3F00 through 3F20. Basically, it's writing all of this data for the two palettes here. And once the palettes are loaded, we do almost the exact same thing for the sprites, where we tell it that it should load the sprite data starting at 0200 and load everything into the PPU like that. So yeah, it's the same basic idea. The loop is a little bit more complex because the sprites are loaded in a slightly different way, but besides that, it's the same idea. So once we have our palette loaded and our sprites loaded, we can finally re-enable NMI on these two lines. We can re-enable sprites on these two lines to make it so that the PPU actually starts running, and then we can sit and wait at jump forever. So this will just sit and wait infinitely. We've loaded all of our data, NMI is ready and enabled. Now we just sit and wait for the NMI interrupt to take over and the game to actually start. So that's all just within the reset. And now what NMI does is it updates the sprite text, the sprites, because basically NMI is called during a vertical blank, and that's when it's safe to move the sprites around without getting things tearing and not looking proper because the TV is in the middle of writing them or anything. So NMI, it starts out by doing a special NES hack called a direct memory interface. This is just a special PPU hack where if you load an address and store it into 2003 and 4014, so you give the lower byte of the RAM address to 2003 and the higher byte to 4014. What the PPU will do is it will look at whatever RAM address you gave it, so in this case we gave it 02 for the high byte and 00 for the low byte. It'll look at that RAM address and just take 64 sprites worth out. So basically, the reason why this exists, and this is the standard way of just dumping sprites from your CPU onto the PPU, this is pretty much how games do it, is because it's only 64 sprites, each sprite takes 4 bytes, so it's only 256 bytes of memory for the sprite data.